Hello everyone, my name is Zerui Guo. I'm a first-year PhD student at UW-Medicine, advised by Professor Ming Liu. My research is mainly focused on SmartNIC assist applications and memory fabrics enabled by CXL. I'm excited to present our paper, LEED, a low-power, fast, persistent key-value store on SmartNIC JBOFs. Nowadays, persistent key-value storage systems are widely used in data-intensive applications, such as web indexing, e-commerce platform, and social networking. A persistent key-value database stores data in the form of key-value pairs, which each key is uniquely associated with a specific value. Its data is typically stored in durable devices like NVMe drives, so the data can survive system shutdowns or crashes. There are three operations in key-value store: get, put, delete, to retrieve, insert, and delete a key-value pair. Traditional solutions construct key-value stores using server JBOFs. JBOF stands for just a bunch of flash. Servers are equipped with beefy processor, multi-channel big memory, massive I/O bandwidth, and tens of terabytes of storage capacities. Therefore, a server JBOF provides high read and write performance, but it comes with the cost of high power consumption. In our test system, it consumes 252 watts under load. Another solution is use ultra-low power embedded storage node, which has been explored by early pioneer systems like phone. As shown in this figure, it uses an array of WinP storage nodes for serving persistent key-value requests. These nodes are divided into front-end server and back-end nodes. The front-end node takes client requests, forwards them to the back-end storage node based on the key hash. The power draw of embedded node is low, to 3.5 to 4.2 watts per Raspberry Pi node, but the single node performance is also low. If serving a request at less than 10 gigabits per second as its design, phone is energy efficient. However, to match today's data center networking speed, which is around 100 gigabytes per second, such design will require a large number of backend nodes and network switches, which adds extra system management capacities. To make things worse, at this scale, it almost consumes a similar amount of power as a server. Recently, a new type of computer device called SmartNIC JBOF emerged on the market. It consists of ARM cores, onboard memory, 100 gigabytes network port, and can connect to NVMe drives through PCIe root complex. A SmartNIC JBOF combines the benefits of server JBOF and embedded nodes. It provides fast networking and around 1600 of key IOPS of random storage access while using little power. For instance, Broadcom single ray used in our test bed only consumed 45 to 53 watts with 4 SSDs on board. It's also cost efficient. SmartNIC JBOFs only cost 1/3 of the price compared to servers with similar configuration. However, the key issue of building key-value stores on this platform is it is extremely architecturally imbalanced. From the memory perspective, memory of embedded node is only 60 times larger than its storage capacities, and 64 times for the server JBOF. However, it's over 1,000th time in the SmartNIC case, which makes indexing value using so limited memory capacity so very challenging. To index a 256 bytes value on the embedded node, we have 16 bytes of memory available, but we have to fit the in-memory index for a key within 2 bits in the SmartNIC JBOF's case. The second challenge is in terms of computing headroom. With high network and storage bandwidth available on SmartNIC JBOF, a WinP ARM core needs to drive 12.5 gigabits per second networking traffic and handle 500,000 storage requests per second to exploit its full potential. This is significantly higher I/O density than both the embedded node and server JBOF case. The third challenge is uneven load distribution. This can be modeled as the balls into the bin problem. A JBOF holds a much larger storage capacity than an embedded node, so it requires few nodes, which each node would absorb a much higher maximum load than the embedded node case. To address those challenges, we propose LEED, a low-power, distributed, and fast persistent key-value stores on SmartNIC JBOF clusters. Our system keeps following goals in mind. First, it needs to be fast and different access patterns. Second, it needs to be fully utilize all the SSDs. Last, it has to be available under node failures. To achieve our goals, we apply following design principles all over our system. The principle 1 is to trade excess I/O bandwidth for scarce computing resource and memory capacities. This inevitably adds some latency but increases the overall throughput. The second one is to make early scheduling decisions to streamline the execution flow of requests. This approach will distribute the right amount of requests to each JBOF and its core, avoiding unnecessary I/O stores. Here is an overview of our proposed techniques. The first technique is a circular log and a hybrid index. A circular log is a continuous space on the SSD, pointed by the head and the tail pointer. We further separate the key log and value log and store key and value separately. Inside the key log, there are segments. A segment consists of one or more buckets where the keys are stored. The offset of the segments are stored in the segment table, and indexed by key hash. We only put segment table in the memory, so with hybrid index, we are able to index a key using on average less than a half-bit memory. However, this approach has its own downside. A get will generate two SSD sites, one for the segment, another for the value. There is where we trade excess SD bandwidth for memory capacities. Similarly, put will request 3 SSS and delete will request 2. We also have batched compaction operation for free up the space for key value. The second technique is to token-based request scheduler. To make every core in our system don't overload by request, we want to make scheduling decision as early as possible. We first get token statics based on the condition of its underlying SSD. Then the scheduler will schedule the requests in the active and waiting queue according to the token. Furthermore, the token mechanism will be piggybacked to the client, which may delay the future request if there is a potential overload happening on the SmartNIC side. The third technique is using data swapping and CRRS. We solve the embedded write within one SmartNIC JBOF. Based on the token statics, the data swapping mechanism is able to monitor the workload between different SSDs. If there is an uneven load, the mechanism will swap the data to another SD that has light traffic. We solve the imbalance rate at cluster level. LEED employs chain replication to provide high availability. We enable all the replicants to serve GET requests, which alleviates the uneven reads problem. If the dirty bit associated with the key is set, this request will be forwarded to the tail node in order to get the correct version of this value. We evaluate our system on the following 3 test beds, and we generate workload using YCSB. In terms of the energy efficiency, LEED outperformed key value by 4.2 times and achieve almost 18 times higher draw carry per joules than the phone case across 6 types of YCSB workloads. We have more evaluation in our paper. So thank you for listening.